Beyblades have always been a nostalgic toy for many. Faint memories of letting it rip still sit in the back of our brains. At first glance, it may look like another toy from the past, but the physics that enables these spinning tops is dizzying. Get it? Anyways, let's get into the creation and physics behind our Beyblade. In a very important 2D momentum lesson, Mr. Florio used Beyblades as an example. This got us thinking about the fun and entertaining toys that uses physics to operate. We then searched how would making a Beyblade be possible without welding metal. Conveniently, the first link we searched up was about a 3D printed Beyblade. We then set our sights on 3D printing, and after finding a simplistic software to model our Beyblades, we began a prototype. And hopefully you can accomplish an in-person Beyblade battle with our 3D printed life-size Beyblades. Before we even start to think about our final model, let's talk about the prototype. There are 4 main pieces that create a Beyblade. Number 1, the outer layer, which is used for impact, protection, and character. Number 2, the underconnector, which is used to help connect the bigger pieces and the smaller pieces on the bottom. Number 3, the tip stabilizer, which grants a flat and stable surface for the tip to spin. And lastly, the spinning tip. This is what allows the Beyblade to spin. The shape of the tip can allow for longer or shorter spin times, as well as faster or slower circular movements. For our prototype, we used a 3D modeling software named Tinkercad to model our pieces. In this clip, you can see the modeling of our prototype's outer layer and underconnector pieces. During the clip, there are 2 key tips that are necessary for any type of modeling on Tinkercad. The first being grouping. Grouping allows for 2 or more shapes to be combined into a bigger shape, as represented by this icon. We use this when attaching our prongs onto the top of the underconnector piece. Our next tip is the use of clear shapes. Clear shapes allows you to trim and remove any part off of an existing shape. Just treat the clear shape as a regular shape and group it in the part that is to be removed. We then exported each individual piece onto an STL file and sent it to the printer. We then used the Ditto Pro 3D printer, which estimates to about $1,900 USD, to print out our prototype pieces. After printing out the pieces of the prototype, it was time to attach the pieces, which had to be glued together. Though it was able to spin, there were many problems with the prototype.
So, the first problem with our prototype, and the biggest problem, was that it did not fit in the ripper. There was no slots to put the prongs of the ripper into, therefore we could not use it to spin and had to hand spin it. The second problem was the glue. Some of the parts that we glued were uneven, and certain parts of the Beyblade had glue unevenly spread across it. We also did not really plan out where we were going to glue on the Beyblade, so certain parts ended up being needed to be glued twice.
To add, the tip stabilizer seemed to burst through the underconnector, which caused the uneven tip, which was another problem. But a positive aspect is the compactness of the outer layer, which provided durability. We reached out to a 3D design instructor whose name was Dan at Maker Labs, which is a makerspace in Vancouver that offers courses for any type of creation. We asked 5 questions about 3D printing and modeling via phone call.
Our first question was, what filament would you recommend for 3D printing? They said it depends on the printer and it depends on the thing you're printing. Our second question was, what is the most common issue when 3D printing? They said making sure the printer is calibrated correctly and making sure the bed is leveled correctly. Our third question was solutions for feeding problems. They said to make sure there's enough filament and make sure the heating temperature is set for the specific filament. Our fourth question was what was the coolest thing about 3D printing that many people don't know? They said it was that you can print custom parts and add-ons for the 3D printer using your 3D printer. Our last question was how to make sure the printing nozzle is at the correct height. They said to move a piece of paper on the bed and move it under the nozzle back and forth. You should feel a slight resistance while still being able to move the paper.
When making an improved balanced Beyblade, it has to incorporate attack and defensive qualities evenly, so I focused on a compact outer layer to sustain hits, and a tip that can occasionally make sporadic moves at around 10 seconds of spin time. The biggest problem I wanted to fix was the ability of the Beyblade to fit in the Ripper, so I cut 2 semicircles in the outer layer, measuring at a radius of 0.8 centimeters to be able to fit the Ripper prongs. And as you can see, I'm making a rounded tip to be able to sustain hits while staying balanced. Now I'm modeling an attack Beyblade with larger spikes to hopefully emulate a one-hit knockout that has a shorter spin time than the balanced Beyblade. The advice Dan gave helped to jumpstart our printing process, as the problems we once had were now solved. And voila! Here's the balance and attack Beyblades after the modeling, printing, and gluing process. Now that we have our final models, let's look into the physics behind our Beyblades. This is the clip that John will be referencing for the period and the radius of the Beyblade.
Welcome to Mr. Nguyen's physics tutorial. Alright, let's find the physics behind a Beyblade. If I ask you to find the centripetal acceleration and centripetal force, what should we do, Mr. Teo?
We should find our givens, which we have. From the center of the Beyblade to the center of the circle of the arena, it is 0.074 meters, and we know that the period is given from the video because it rotates 0.92 seconds. So now we should look for the acceleration.
That is correct. What should we do next, Josh?
Use a circular motion formula.
Okay, so once we use the formulas to find acceleration, we get 3.45 from that, meters per second squared. Then, in order to find the force, what should we do, Josh?
You can use the Beyblade and measure its mass.
Good. We have the mass, which is 0.01 kilograms. When we calculate it, we get 0.038 newtons. Good job, everyone. We found the physics.
Great job!
3, 2, 1, go!
I'm ready to beat Ryan in a Beyblade battle.
I'm tasked with the attack Beyblade.
Whereas I'm attacked with a balanced Beyblade. This is going to win.
Alright, so it's a best of 3, so first to win 2 rounds wins the whole thing.
3, 2, 1, let it rip!
Let it. No!
When comparing the uniqueness between our new and old models, not only can the new model be spun through an actual ripper, our new model's outer layer can detach from the smaller pieces rather than needing glue. When determining uniqueness from original metal Beyblades, our Beyblades are almost 5 times lighter than the 49-gram metal Beyblades at 11 grams. For the advantages of our balanced Beyblade, the compactness allows for steadier movement and better balance. The ridges along the outer layer can deflect any oncoming hits as seen in the fight, and the detachability can prevent the prongs in the underconnector to break and saves a bunch of glue. For the disadvantages of our balanced Beyblade, the grid-style printing in the Beyblade caused the sanding in our ripper holes to look messy. The depth of the ripper holes prevented the ripper prongs to go all the way, as it could only make it 3/4 of the way. And the filament used on the Beyblade made it hard to see on our Beyblade table.
Alright, Mr. Florio. For the advantages of our attacker Beyblade, the weighted spikes dealt greater hits to the opposing Beyblade, as well as the weight of the outer layer provided greater force and momentum when it moves into contact. The diameter of the outer layer takes up more space in the arena, forcing the opposing Beyblade to fight in a less ideal condition. As for the disadvantages of the attacker Beyblade, the outer layer may provide more momentum, but the weight of the outer layer creates an imbalance with the smaller parts, which then reduces the spin time. The height of the attacker Beyblade also puts itself at a disadvantage, as the opposing Beyblade can strike the underconnector and put the attacker Beyblade off balance. The glow-in-the-dark filament is also a visual disadvantage on our Beyblade table.
If Mr. Florio were to challenge us by recreating our Beyblades, more careful thought in the mass and height distribution of not only the overall Beyblade but individual pieces like the outer layer would hopefully increase the spin time on both Beyblade types. To add, having the 3D printer print the filament in a circular printing style rather than a grid style would help the sanding process and any other adjustments look smoother. And lastly, using a more colorful filament would add more pop to the cosmetic aspects of our Beyblade and hopefully make them more visible on the arena. Thank you guys so much for watching.
Great job!